Hi, I would like to present you a recent research that me and my supervisor, Dr. Kutsabas Panayotis, have conducted, in which we present and compare two interaction models that support mid-air gesture manipulation of multiple targets in the same physical space. From our recent review of papers that examine mid-air interaction, we saw that most of them deal with a single device. They use a small set of gestures, and they focus either on design, which is the process of crafting gestures for controlling a device, or focus on evaluation, which is the process of measuring various aspects of user experience and usability, such as gesture appropriateness, fatigue, memorability, discoverability, comfort, etc. Given the constant research interest in mid-air interaction, there will be some cases when multiple gesture-enabled devices will be placed in the same physical environment, such as a smart home environment. In general, there are five design challenges when designing novel sensing user interfaces, and these are address, attention, action, alignment, and accident, as noted in Belotis et al. Work in 2002. In our research, we focus on three of these challenges. The first one has to do with address and commands. When multiple appliances are placed in the same environment, the user should be able to address the desired device before commanding it. Therefore, the challenge here is to enable device addressability with mid-air interaction. Memorability. Mid-air interaction with even a single device requires a user to remember several gestures. As the number of devices increases, so does the gestures that the user will have to remember. And as that number increases, so does the cognitive load of the user. So the challenge here is how do we keep the gesture set as small as possible in order to enable memorability. The third challenge that we examine here is about mid-stats phenomenon. It is known that mid-air interaction is prone to mid-stats phenomenon, which is the phenomenon of activating a command unintentionally. The problem is more intense in the case of a smart environment with multiple devices that might be placed next to each other, or there are similar gestures commands, or there are similar gesture commands for different devices. So the challenge here is how do we avoid these accidental operations on nearby devices? To address these challenges, we present, examine, and compare two interaction models that allow mid-air interaction with multiple devices. The first one is called address then command interaction model. Basically, it's about a two-phase interaction in which in the first phase, the user from a relaxed position performs an address gesture that corresponds to the desired appliance. Then, in the second phase, the user will have to perform another gesture, which is the command gesture that will trigger the appropriate command on that device. I should note here that between phase one and phase two, we have set a time limit of 5 seconds in which the user will have to perform the command gesture. If no command is provided by the user, then the addressed device, returns to the idle state. The second interaction model is called address end command. Basically, it's a single phase interaction in which the user uses his or her non-dominant hand to perform a posture that will address the corresponding device. And as long as he performs that posture, he can perform a gesture with the dominant hand to trigger the corresponding command on that device. The figure here illustrates an example of increasing the volume on the TV. First, the user is in a relaxed position. Then he uses his left hand, non-dominant hand, to perform a posture that will address the TV. And at the same time, he performs a gesture with his dominant hand that will trigger the command on the TV. When the user returns to his to a relaxed position, then all the devices return to idle state. I should note here that while the commands are triggered with either a gesture or a posture of the user's dominant hand, to address a device, the user is only allowed to perform a posture. This is because the user wouldn't be able to perform at the same time two different movements with his hands. So we limited the address with a posture and the command with a posture or a gesture. In order to examine and compare these two interaction models, we conducted two case studies, one for each model, that include identical gesture design technique in order to construct a user-defined gesture set for each interaction model, a similar working prototype with a spatial augmented reality technology, and an identical evaluation technique to measure various aspects of user experience and usability. To produce natural and contextual relevant gestures, we conducted a frame-based elicitation study. The frame consists of several limitations that were explained to the users. These are general limitations. For example, that we have 7 devices, which are TV, MP3 player, movie player, speakers, air conditioner, blinds, and lights. The commands are common among more than one devices. All devices are placed in front of the user, and the user can be seated or standing. Also, other limitations are imposed by the corresponding interaction model. We asked from 18 users to participate in our elicitation study. In this study, each command and device was shown to the participant as an abstract icon. There were 12 commands, and most of them were common among the devices, and 7 devices. These abstract icons were shown as a slideshow presentation. For each one of them, command or device, participants were prompted to propose the most appropriate gesture. And at the end, we had about 342 proposed gestures for each interaction model. To construct the final gesture set, we took these proposed gestures and we further analyzed them with the level of agreement metric. So we end up with the final gesture set for each interaction model. To test and evaluate the gesture sets for each interaction model, we implemented a working prototype that consists of various technologies. To implement the functionality of gesture recognition, we utilized Microsoft Kinect and machine learning tools. We used Kinect Studio and Visual Gesture Builder to record, define, and test each gesture. The outcome of this process was a gesture database which includes all the necessary information for gesture recognition. That gesture database was then imported into a Unity 2D project. The Unity project includes all the functionality of the devices and provides visual and audio feedback to the user, which is triggered after a corresponding gesture is recognized. Now, in order to create a more realistic prototype, we also use spatial augmented reality technology. We first created some mock-ups and placed them in the physical space. These mock-ups came alive with projection mapping technique. For that purpose, we used MadMapper software that uses the Unity project as input and streams it onto the mockups through a ceiling-mounted projector. Finally, during the evaluation, some help videos were displayed onto the wall in order to help the user. These videos were created with Blender software, and the playback was controlled by the researcher through an iPad. The evaluation method consists of 4 sessions: learning, recap, testing, and questionnaire session. We asked from 19 users to participate in the address then command use case, and from 17 users to participate in the address and command use case. We did a scenario-based evaluation, and there was a script with 36 tasks or commands that the user had to complete. Each task was narrated first by the researcher, then a help video was shown to the user in order to instruct him how to perform the gesture correctly. And then the user was prompted to perform that gesture in order to trigger the command. In the next session, the recap session, we did a semi-structured interview with each user. Each one of them was asked to reproduce the correct gesture for each command. That process helped us ensure that the users have understood and learned the gestures, and also allowed us to remind them those gestures that they couldn't recall. The next session, the testing session, was identical to the learning session, with the only difference that no help was provided to the user. Okay, let's see now the results from our evaluation. First of all, the overall task success was very satisfactory in both interaction models. We can conclude that although our system was an early prototype, these high rates of task success are indicative that mid-air interaction with multiple devices is feasible, since users can operate it effectively. Task time. Task time corresponds to the period between the time the task was narrated to the user until the time the system responds to the gesture. Task time for both interaction models was fairly acceptable, with address and command being significantly faster. We believe that task time is acceptable, and also in the long term, users will perform faster if they continue to use the system. False negative errors. False negative errors occurred when the user performed the gesture correctly, as judged by the researcher, but the system did not respond. Address and command interaction model produces less false negative errors, and it can be further reduced if we apply more extensive gesture training with the Visual Gesture Builder software. False positive errors occur when the user performed a gesture and the system responded incorrectly, or when accidental activation of another device took place, which is the Midas touch phenomenon. As we see here, false negative errors were very low for both interaction models. So we can conclude that the restrictions of both interaction models kept false positive errors very low and almost eliminated the Midas touch phenomenon. Memorability was measured during the recap session. Both interaction models have a high memorability rate, and we can conclude that the 19 gestures, which can be translated to 34 different tasks, were easily memorable by most users. At the end of the evaluation, users had to fill in two questionnaires, the System Usability Scale and the User Experience Questionnaire. From their responses, we see that user satisfaction was very high for both interaction models, but address and command scored slightly better than address than command. So, what are the conclusions from our research? As I said earlier, we mainly focus on three design challenges. How do we address and command multiple devices that are placed in the same physical space with mid-air interaction? How do we keep the gesture set as small as possible? And how do we minimize the Midas touch phenomenon? We saw that both interaction models support addressing then or and commanding multiple devices and allow users to operate them effectively, directly, having no graphical user interface, using only mid-air interaction. Also, the concept of address and command device allows us to have reusable gestures. Having reusable gestures offer the advantage of having to remember a small set of gestures in order to control many more operations of the system, which in turn facilitates memorability. And we saw that both interaction models scored high memorability rates. Also, both models had very few false positive errors, which indicates that Midas touch phenomenon was not apparent. So in general, both models were almost identical in terms of user experience and usability. However, even though the address and command interaction model requires compound body movements with the left and the right hand, it appears to be faster than address than command. Thank you for your attention and your time.